today's goal of this lecture. Today I will see some question about analytic function and zeros of analytic function. This question, first question, had come in GATE exam. The question is, if the real valued harmonic function on the complex plane satisfied the Laplace equation fxx plus f of yy equal to 0, then the function g equal to fx minus I fy and a is equal to fx plus I fy, then option 1, both g and h are analytic. Option 2, g is analytic but not h. Option 3, h is analytic but not g. Option 4, neither g nor h is analytic. Here given the function g equal to fx minus I fy. Here consider this is u and minus iv. Then ux equal to f of xx and uy equal to f of yx and v equal to minus f of y. Then vx equal to minus f of xy and vy equal to minus f of yy. And according to CR equation, notice ux equal to, according to CR equation, ux equal to vy, that means f of xx equal to minus f of yy, that imply f of xx plus f of yy equal to 0. And this is the condition of harmonic equation. And another equation of CR equation is uy equal to minus vx. Then f of yx equal to f of xy, and by Young's equation we all of us know this is always true. Therefore, since this is satisfy the CR equation, so G is analytic, this is true. Here is A is analytic. Here given A is equal to fx plus I fy. This is u and this is iv. Then ux equal to f of xx and uy equal to f of yx and v equal to f of y. Then vx equal to f of xy and vy equal to f of yy. Therefore, by CR equation ux equal to vy, that means f of x equal to f of yy. This is not harmonic equation. Also uy equal to minus vx and uy means f of yx. f of yx equal to uy equal to minus vx equal to minus f of xy, and this is also not Young's solution. That means this is not satisfied. Harmonic equation also Young's theorem. So A is not analytic, but G is analytic. So option 2 is a right option. I hope my all viewers have understood this question easily. Okay. Well, this is a very important question, but this question depends on just basic knowledge. Okay. Next question. Let's see the latest question. Next question. Let f be entire function. Then which of the following statement is false? Here notice, here the question about which of the following statement is false. Option 1, real fz and imaginary fz is bounded, then f is constant. Given real fz imaginary fz are bounded. This is the given. That means there exist m1 and m2 such that real f less than equal to m1 and imaginary f less than equal to m2. Then mod fz, which is equal to real f plus imaginary f and this is the complex function. This is real f plus I times imaginary f, and this is less than equal to mod real f plus I times imaginary f, and this value real f less than equal to m1 and imaginary f less than equal to m2. That means this is less than equal to m1 plus m2. That means since mod fz is less than equal to m1 plus m2, that imply fz is bounded function. And given f is entire, and we all of us know entire plus bounded, that imply f is constant. So if real fz and imaginary fz is bounded, that imply f is constant. Option 1 is a right option. Option 2, if e to the power real modulus of real fz plus imaginary of fz is bounded, then f is constant. Next question, if e to the power real f mod real f plus imaginary f is bounded, that means obviously real f plus imaginary f are bounded. That imply fz is constant function. So this is also right, but notice here question about which option is false. Option 3, sum of real f plus imaginary f and product of real f plus imaginary f are bounded, then f is constant. For this, consider fz equal to real f plus I imaginary f and mod fz whole square, means real f plus I imaginary f whole square. This is means modulus of real f whole square plus modulus of imaginary f whole square. And this means real f whole square plus imaginary f whole square minus 2 real f imaginary f. That means given sum of real f and product of our real f and imaginary f are bounded. Since this is bounded, and this is bounded, that means whole part is bounded. And since fz is entire function, that means entire plus bounded, by Liouville's theorem this is given constant function. Option 4, notice option 4. Option 4, if sine of real fz plus imaginary fz is bounded, then fz is constant. Consider fz equal to z, which is equal to x plus iy, and sine of real f plus imaginary f means sine of x plus y, and given this is less than equal to 1, that means sine of real f plus imaginary f is bounded. Since this is bounded, that means fz equal to z. Is it constant? No. Here fz equal to z. This is the polynomial function. This is not constant, but sine of real f plus imaginary f is bounded. But this is bounded, but fz equal to z is not constant. I hope my all viewers have understood. Even if sine of real fz plus imaginary fz bounded, then fz is constant. That means option 4 is a right option, because only this option is false. All options are right option. So, since the given question has indicate which of the following is false, that means option 1, option 2, option 3 are all false option. Only all right option, here false. Here only true option is 4, because here the question about which of the following is false option. Next question. Consider the following condition. Modulus of fz equal to 1 for all z belongs to C such that imaginary z equal to 0. Then which of the following is correct? Option 1, there is a non-constant analytic polynomial which satisfying the condition P. Option 2, every entire function satisfying the condition P is constant function. Option 3, every entire function which satisfying the condition P has no zeros. Option 4, there is an entire function which satisfying the condition P with infinitely many zeros. For this, consider non-constant analytic function e to the power iz, which is equal to e to the power ix minus y, and modulus of e to the power iz means e to the power ix times e to the power minus y, which is equal to e to the power minus y, which is equal to 1 on imaginary z equal to 0. That means every entire function which satisfying the condition P is a constant function, this is the wrong option. This is non-constant function, but this not satisfy the condition P. So option 2 is a wrong option. Option 3, every entire function satisfying P has no zeros. This is right option. At first I will see option 1. There is a non-constant analytic polynomial satisfying the condition P. Suppose let F be non-constant polynomial such that fz equal to an z to the power n plus an minus 1 z to the power n minus 1 up to a naught, and if imaginary z equal to 0, then fx equal to an x to the power n plus an minus 1 x to the power n minus 1 up to a naught. Just common x to the power n, then this value would be a to the power n plus a to the power n minus 1 over x up to a naught over x to the power n. And as limit n tends to infinity, fx, this value is equal to infinity. So every non-constant polynomial not satisfy this condition. So option 1 also wrong option. There is an entire function satisfying P which has infinitely many zero in C. This is also wrong option because I have got for this function which is satisfying P, the condition P, but it has no zeros. Option 3 is the right option. Every entire function satisfying P has no zeros. Obviously this is the right option. For this, since given modulus of fz equal to 1, then that imply fz times fz bar equal to 1, and this is imply fz times fz bar equal to 1. And notice both are entire function. And these are entire function since on imaginary z equal to 0 means on whole x-axis. Since whole x-axis be the limit point which belongs to the complex plane, so fz times fz bar equal to 1 by identity theorem, this is true on whole complex plane. So every entire function satisfying the condition P has no zeros, because since this is true, that means the function has no zeros. So option 3 is the right option. I hope my all viewers have understood. That means since it has no zeros, that means infinitely many zeros, this is the wrong option. That means only option 3 is the right option. Today I will stop here. In my next video I will discuss complex integration, complex integral. This part is very important also for any competitive exam. Okay. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.